Hi everyone, my name is Matt Gooding and I'm a software engineer working on Bentley's iTwin platform. Today I'm going to be talking about how to connect the Unity game engine to the iTwin platform. Hopefully if you're attending this webinar you have some familiarity with the iTwin platform already, but briefly, it's Bentley's solution for aggregating data from disparate engineering sources together in a common API to facilitate the creation and management of digital twins. For more information, please visit our website at developer.bentley.com. And to find more information about the particular APIs that we're going to be talking about today, you can go to iTwin.js.org. Now, you may or may not already be familiar with the other part of today's presentation, the Unity game engine. Unity is one of the most popular game engines along with Unreal. It's very popular with game developers, but it's also widely used in the AEC space. There are a few reasons why. Unity provides a common platform for many devices, including augmented reality, virtual reality, desktop, mobile, and many niche devices like caves and others. It has an intuitive programming environment. You write your programs in C#, and there is a lot of excellent tooling from Visual Studio, JetBrains, and others. It has a really strong ecosystem for gamification and simulation via its asset store, where you can find lots and lots of plugins along with code extensions and kind of whatever you're looking for. It's also developed a very robust free and open sourced ecosystem. If you search for Unity on GitHub, you will find lots and lots of very well maintained and popular projects to extend Unity in lots of different directions and provide a lot of common functionality that might not quite be in the engine yet. And the other big positive point for leveraging Unity is that it's become, along with Unreal, one of the defaults for doing high-level 3D development. If you are integrating with a new device or 3D platform, very often there is a Unity SDK available for it. Microsoft has done a lot of great work making this the easiest way to develop for HoloLens, both with the base SDK, the MRTK library that provides a lot of interactions and UI elements, the Azure Remote Rendering Service, which natively ties in and lets you render enormous models, and lots of other third parties integrate as well, like Mapbox and whatnot. So, what makes the iTwin platform and Unity a good match? Well, I think I described why Unity is appealing for AR, VR, and those other use cases. iTwin is a really ideal way to feed your Unity application with AEC data. We aggregate from many different AEC file formats, many of which lack an existing pipeline to Unity, and even in the cases where there may be an existing pipeline, it can be very, very slow. The aggregated data maintains its original geometric representation. It's not just meshed at some predetermined level. We have spheres and cones and surfaces of revolution and B-reps and B-splines and all of that good stuff. And this aggregated data maintains its intelligence. All of the business properties and the metadata are persisted into the iModel's base infrastructure schema, or BIS. So you're able to query many data from many different file formats and display data from many different file formats using one common API. And the really nice thing is the iTwin platform is, in particular iTwin.js, is offered as a open source API for Node.js So you can use it, as we will in the sample I'm going to show you, as a headless API that can either run locally on your machine or on a server. You may have seen some other solutions that require you to have the design application open in order to query information from it. We don't need to do anything like that. Our users don't need to have anything special on their machines. And even though you can run this on a server in a connected workflow, you can also run Node locally, disconnected, or on a closed network. Say you were at a trade show or something, and you wanted to stream to a device. So it really is kind of the perfect way to feed your application. So in today's webinar, I am going to be walking through our open source iModel Unity example on GitHub and explaining how it works. I'll show you how to extend this example for custom use cases, and I will talk about how you might leverage the capabilities of iTwin.js to optimize performance for your application. By the end of the session, you should be able to make a demo Unity application that streams in your iModel data on any platform that Unity supports, including AR and VR devices like the HoloLens, Oculus Quest, HTC Vive, you name it. So let's get started. So the first thing that we need to do is to clone the repository for the example from GitHub. You can find it at github.com, iModel.js, iModel Unity example. So I'll copy the URL to my clipboard, open my command prompt, and pull it down. Okay. After you've cloned the repository, you can navigate to the Node subfolder in the repository. And I should note that this project has the same base requirements as the iModel.js monorepo, so you need Node 12 in order to do this. The other requirement that we have is obviously you need Unity. The project depends on Unity 2019 or later. I'll be using Unity 2019.1 in this case. That's what I happen to have on hand, but any 2019 version or 2020 version, etc. should work as well. Okay, with a command prompt open, type npm install to install the necessary npm packages. All right. npm run build in order to compile the program. And then npm start in order to launch the server. Great, we're up and running. Now, the next thing to do is to open the Unity Hub. Find your project. Select the Unity subfolder. This is the directory that will actually be recognized as a Unity project. And we're off and running. Well, we're off and importing anyway. All right. Application is loaded. Resize my window to fit into the recording area here. All right. Now, important thing to do is we need to open the actual scene. Unfortunately, I can't specify in the project which scene to start with. Once we've done that, we can push play, and voila, we've connected to the server, and we are streaming in our iModel data. And if I switch back to my console window here, you'll see we have lots of information about what's happening as we're rolling along. You can see when I connected, my requests in order for setting the data up, and then my requests for all of the meshes that went through. And we'll go into all of this in more detail later on. But this gives you an idea of just how easy it is to get this up and running. And again, all of this is not pre-meshed data. This is all streaming from the real file, the same one that you would open in any of our samples that use our traditional web technologies. It's all created on the fly and streaming in. Okay, so this was done using a local snapshot file. If we wanted to use something from iModelHub, there are a few more steps to go through. So let's go through that next. Okay, the first thing that we need to do is go back to our code. So in the node subfolder, there is a file called iModelHub download.ts. At the top of that file, you'll find this iModelHub request props, along with a command to specify your own context ID and iModel ID. We also have a link to the iTwin.js getting started registration dashboard, where you can find any sample projects that you've used previously. So let's open up that page. So I have some projects that I've pre-populated here. You also could create your own with our samples. Use a local file. It can be a DGN, DWG, or a Revit file, or use iTwin Synchronizer. And if you're using iTwin Synchronizer, you have lots more options. You can leverage any of the file formats that we support, which is a very long and growing list, as you can see. Okay, but for now, we are just going to use one of these. So I'll click on Show IDs, copy, go back to my code, paste that in. Now these are formatted for the environment variable method that some of the other samples use. So we just need to paste them into JavaScript object. Okay, clear those out of there, save, and then go back to the command prompt, stop my server, build, okay. One thing that I need to do differently now that I'm using the iModelHub with the sample is, instead of typing npm start, I'm going to type node libmain.js. And again, all of these instructions are part of the README for the GitHub project. Okay, so it's telling me that I'm not using a snapshot. I'm opening from iModelHub. It's attempting to sign in. I actually have my sign in cached. The first time that you do this, it will ask you to sign in, and then your sign in will be cached for the next 30 days, so you shouldn't need to do that again. I actually have used this previously in testing, so it had found that I had this briefcase cached, and it's using the local copy, and you can see my server is now running. So let's switch back to Unity. You can push play. And we're streaming in this building sample. You'll notice that this model has textures and that those come through without any issue. And yes, these red blocks really are in the model. We would probably want to use some filtering in our graphics select query in order to take that out. I'll talk about that a little bit later on. Real quick, let's just pick another project so you can see how easy it is to swap these in and out. All right, so again, I'll stop my server, go back to the registration dashboard, and this time we'll pick a larger project, the metro station model. Copy that to the dash clipboard, paste that in. Right. And again. We'll start up our server. Okay. And this time we don't have this one cached, so you'll see the download message come through. All right, and we're all set. Go back to Unity. All right, now this is a larger model, so the graphics will continue to stream in over a longer time period. But while it's streaming in, you can see that it's still interactive. I'm able to fly around. Yeah, no floors yet. Yep, they're coming. Filling in bit by bit. There we go. Okay, now that we've shown the basics of how to pull data from iModelHub, let's move on to talking a little bit about how this all works. Okay, so we'll start with the high level and then drill into some relevant details. The first thing to understand is that connecting the iTwin platform to Unity requires two separate processes. This is because iTwin is a JavaScript, TypeScript only API. It needs to run on JavaScript engines like Node.js or one in your browser. So in our case, we have a Node.js process running the iTwin.js code and a Unity process running some standard Unity code. If we have these two separate processes, then we need some way for them to communicate. For this example, I chose to use WebSockets, which is an efficient communication mechanism that works well whether the two processes are on the same computer or on multiple devices. This lets us easily adapt the sample code for running purely on our desktop or connected to a standalone device like the Microsoft HoloLens or Oculus Quest, or if you had a remote server running, providing the data to your local desktop application. Really, any scenario is possible with this setup. Okay, so if we have our two processes and we have our communication mechanism, the last thing we need is a format for that communication. And in this example, I chose to use protocol buffers for that. Protocol buffers are a way to define a message schema and then have code generated for lots and lots of different languages that leverages that message schema. They're very efficient, But the really important thing is just having broad support. We want to be able to go from our iModel.js code to Python, C#, C++, et cetera, et cetera, et cetera, and have matching typed code that we can use to improve our velocity of getting work done. You can see an example of this here on Google's site. They have the .proto message definition. They have what appears to be some Java code that writes one of these messages, and then what looks like some C++ code that reads it in. And you'll see that we have something very similar in our example once we get a little bit further along. So let's go back here. So putting it all together, the iModel Unity example is a Node.js process running iTwin.js backend code, a Unity process connected to that Node backend via WebSocket, and then the two processes are sending messages to each other encoded as protocol buffers over that WebSocket. The Unity process always initiates these messages. It sends them encoded as requests. The Node process always sends back one or more messages, which we term as replies. And that's pretty much it. Next, we'll step through adding a new request-reply pair, which will help give you a concrete understanding of how this all works. Just briefly, I'll note that this system is very similar to and inspired by gRPC. I didn't actually use gRPC because the Unity support was very new when I did this, and the TypeScript support was actually not really there. You didn't get actual type definitions for any of your messages, which I thought kind of defeated the point. These days, gRPC might be a better answer if you're so inclined. If you choose to do that, the system would port very cleanly over to it. The request-reply thing is basically a gRPC service. Okay, so next we'll move on to looking at defining these request-reply pairs in practice. Okay, so we've opened up our iModelRPC.proto file in the Node subdirectory of our project. This is the protocol buffer definition file. You'll see at the top it has this request wrapper message type and this reply wrapper message type, and that both of them have this request ID field, along with both of them having a message field with different nested types of messages. So the request wrapper is what is sent from Unity. It has an ID to pair these so that when the reply comes back, it knows that the reply went with X request. It has this message field so that we know what kind of message this is. This one of marks this as only being one of these at a time. And we need this because protocol buffer messages are not self-describing. So if you don't have a wrapper like this, you wouldn't know what you were receiving. Okay, so in order to add another type, we need to put it in here. So let's put in example request and matching example reply. This is all just standard protocol buffer language work. If you look at the protocol buffer documentation, you'll see how to do all of this. There's plenty out there, lots of tutorials and whatnot. All right, so now that we've added these, let's add the actual message types at the bottom of our file. And we'll put in kind of a dummy field so that we can verify this working. We'll say that our example request is going to ask for some text to be repeated back. And our reply is going to do that repetition. Okay, once we've put this definition in, then we can go back to our command prompt and run the proto build command from inside the node subdirectory. This is a node command that I've written to generate the JavaScript code, the accompanying TypeScript definitions, and the Unity code that goes with our protocol buffer. So now, when we go to the protobuf RPC server file in the node subdirectory, you'll see that there are different request handlers for the types of messages we're already able to do. So we just need to add in one for our new example request. Okay, so now we need to define that method. I'll go down to the bottom of this file. And go example request. And you'll see that all of these take the form of socket, iModel, although in our case we won't use the iModel, so I'll put the underscore and keep the linter happy, and request wrapper, which is just the TypeScript class for what we just generated from our protobuf definition. Okay, so to actually handle this request, I'll delete out my copied code. Let's find it in the field, and you'll see that our VS Code IntelliSense has picked up the field we added. So we'll say we're going to be using the example request. We will assert that that is always defined. We know this function is only called if this is defined. So again, this is just keeping our linter happy. Find the repeated text in that definition, and we will make sure it's actually repeated. So this is our request type, text to repeat, and we'll put that in there again. Now, once we have that, we need to send back our message. So you can see there are a few different parts to one of these. The first thing is the socket, where we'll actually send the data, and then there is the reply wrapper object, but when we send it over the socket, it needs to be encoded as just a uint8 array. So we have some helper functions to do that. So let's start from the reply. So our example reply needs to fit the form example reply. And this is again our generated code matching up with this guy. So our example reply will have the field repeated text. And you know what? Let's actually make that inline. Grab that out of here. So that satisfies the form of the example reply. And now we need to encode it. So we'll make an object called encoded reply. We use our helper encode reply function. We need to have the request ID so that when Unity receives this back, it knows what it goes with. That's on the wrapper object. And then we need our iReply wrapper object. So we can put the example reply in there. And then we can send it back via the WebSocket. And that is everything we need from the TypeScript side in order to handle this message. So now if I go back and build this. All right, we are all set. Now, we need to go over to the Unity side and handle actually sending this message. So let's go into the Unity subfolder, Unity assets, Bentley scripts. Main loop.cs is the function or file we want. In here, there's the update function. This is what Unity calls on every frame. And we'll add in kind of a hacky thing, just waiting for somebody to push the space bar. And I usually do my Unity code editing in actual full-on Visual Studio. The IntelliSense is much nicer than what you get with VS Code. But for now, I'll just do this here in VS Code to stick with one editor. Okay, so when the user pushes the space button, what we want to have happen is for them to send that example request that we just defined. So here in our Unity code base, we have this member called backend, which handles the routing of these messages. So it has a message to send, a request, and we define a request wrapper. We put in the example request field. I'm actually going to move this back so we have a little more space. And I will say my text to repeat equals pizza. So on the Unity side, we send the first object is or the first argument to this function is a request with the request type along with any parameters for it. And the second argument is a function to call when the request is fulfilled. So from that, in that callback, you get this reply wrapper. And the reply wrapper matches up with, I'm going to put the Unity engine, keep this happy, matches up to the protocol buffer definition file. So it's going to have an example reply field with our repeated text. We'll just log it to the Unity console when we receive this. And that, I think, will do it. A little bit tricky doing this without Visual Studio when you're used to it, but I think I've got it right. Let's see. Compiling my code. Okay, it's satisfied. All right, so let's go back. Make sure our node code is compiled. And we'll just start up with a snapshot. I want a smaller model for showing this since we're not doing anything with the model, and I want to have my log window have less data in it. Okay, so our backend is started. We've loaded this model. And now if I push, my camera so I can deselect. If I push space, you'll see I get my repeated pizza message. So every time I'm doing this, I'm sending something to the back end, it's getting it, doing the work, then calling back into our Unity process. And you can see the logging that we have in the node process is telling us about the messages it's receiving. Okay, that is the basics of adding a new command. Next, we'll go through and look at some of the commands that are already there. Okay, our first command is the project extents request. This is pretty simple. All it does is ask for the total range of everything in the iModel and send it back over so that on the Unity side we can shift all of our coordinates to fit within Unity's single float precision. If you've worked with Unity and CAD models before, you've probably brought something in that was very far from 0, 0, 0 and seen your geometry flip out all over the place. We do this to easily prevent that from happening. You can see on the iModel side what this looks like is pretty straightforward. Project extents request. Yep. So we get this, we look at the project extents property on the iModel, and we send back the needed information. And then on the Unity side, if we look at coordinate utility CS, you can see how we send this. We talk to the backend, send a request. Our request wrapper identifies it as a project extents request. There are no parameters. Our callback function receives the reply. The reply has the min, the max, and defines what we need in order to convert our coordinates. Next, let's talk about the camera views request. So this is another request with no properties. When we send it, we just know we want to get all of the view definitions that have the camera property on. And if you look at it, the function that handles it, that's exactly what it does. Uses ECSQL to query the view definition 3D class, gets the element, and then checks if the camera is on. If it is, it sends back the information about the camera, its display label, its orientation, and its actual position. This is one of the streaming reply types that I mentioned before, the one-to-many. So for every view definition 3D we find that has the camera on, we send a separate one of these messages. And then when we're done, we send a empty reply to say, hey, this is all of the responses that you're going to get for this request. And then if we look on the Unity side, you can see how this is started. We do send request, no properties, and rather than specifying an anonymous function, we specify an actual delegate function here. And you can see how this checks if there are any more streaming replies coming in. But yeah, it uses the information and saves these off so that you can toggle between the views once you have them in. Okay, and next let's look at the texture request. This one has one property, which is the element ID of the texture, and sends back two things. One is the texture ID so that we know what to name it on the Unity side. And the other are the bytes for the texture data, which I believe is a JPEG, if I'm remembering right off the top of my head. Let's see, handle texture request here. So we query for that element. The element we get back has the texture element we get back has the bytes for the image stored as data, and that's what we send back. And then on the Unity side, This is used in texture cache, which stores the data for each element ID so that we don't need to send multiple requests. But you can see we use this while loading the geometry. We're able to create a stub texture. We fire off the request, and then when the data is received, our callback function fills in the texture for us. Okay, let's look next at the tooltip function. So this is what we use when clicking on an element to display a little bit of information about it. So this sends element ID, Unity sends element ID, and then our node process sends back the element ID, the class label, the category label, and the model label. So let me show what this looks like. Oops, not the one. Let me show what this looks like in Unity real quick. So when I'm clicking on things here, you can see I'm getting back this information. This is done. All of the elements we pull in have the name set to the element ID, and then we have a mesh collider on here. So I'm able to use basic Unity functions to figure out what's under the cursor, send the ID over, get the information back, and display it here. All right, in the interest of time, I won't show the code for that. Let's look at the select element ID requests. So this sends a select filter. I'll show what this looks like in the node code in a second, and then sends back a array of element IDs. That's what this repeated field means. So if we look at handle select, you can see our base is select EC instance ID, and then we concatenate whatever the select filter is. And then we send all of that back over to our Unity application. So this is a very generic request you could use to do lots of different things. We actually use this for controlling the graphics that are streamed in. You might have noticed that as I moved my camera around in Unity, it seemed like new things would come in as I moved around, and that's exactly what's happening. We use EC-SQL spatial queries in order to figure out what elements are in the view, and then request the meshes for just those elements. So this is step one of that. We request the IDs. So this is the actual filter being put together. Here's the request for them with the callback function. And then where these are actually used is in the last and most complicated command, which is export meshes. So export meshes, the request is actually pretty simple. You send it an array of element IDs and then a tolerance for how finely meshed you want the graphics to be. And then you get back the element ID of the mesh, the color for the material, how many, and then this is some information about the mesh, the index count, the vertex count, and the mesh data. I'm going to run out of time to get into what this actually is, but basically the mesh data is stored in a way that's very fast for Unity to process. Let's see, where do we do that? Element mesh reader. We get that data back, and I use the Unity job system and some of their nice functions that don't perform allocations in order to get it in without generating garbage and dropping frames and all of that. And I think that's all the time I'm going to have to, actually, real quick, let's export message request. So the one thing I wanted to mention is all of this is based on the export graphics API inside of iTwin.js. This is what we use for exporting GLTF, exporting out to LumenRT under the hood. Lots of different things use this. If you look at this API, it can do some things that aren't in the Unity sample yet. So if you're looking to connect to iTwin.js with Unity or any other platform, this is where I would start personally. Okay, and with that, I think I'm going to have to move to wrapping this up. So unfortunately, I haven't been able to get through everything that I was hoping to today, and I'm just about out of time. But real quick, I wanted to hit on a few things. One is, if you've watched this presentation, you may be wondering, how do I deploy this to Oculus Quest or HoloLens or any other platform? The answer is you do it the way that you usually would in Unity. You just pick your platform and go. There's nothing in here that prevents this from working on UWP or Android, the platforms for HoloLens and Oculus Quest. There are minimal dependencies, and the dependencies that are there, we verified, do work on those platforms. The other thing I wanted to mention real quick is the performance of this out of the box is not going to really scale to big iModels. And that's because we're creating individual game objects for every element in the interest of simplicity and flexibility. In a real application, you would want to batch together data or perhaps really restrict how many elements you load in at a time, depending on the platform. There's more information about that in the Unity applications README. And if you have any questions about this or any other part of the example, I'd encourage you to post it on our GitHub discussions page. We're actively monitoring and very interested in helping out.